Hello students, welcome back. We just went through a couple of problems regarding standard normal random variables, one in forward direction, the other backward. Now let's discuss some theoretical foundation about this and then set the stepping stone toward the next level, the application problems. Recall the standardization theorem. We went through this already previously. Given random variable x with mean mu and standard deviation sigma, we can define a new random variable, a composite random variable, z as x minus mu over sigma. Then that new random variable z has expected value 0 and variance 1. So the standard deviation is also 1. The proof was actually pretty simple. If you recall the expected value of ax plus b form and the variance of ax plus b form, here a is 1 over sigma and b is minus mu over sigma. But how do you get those expected value and variance of ax plus b form? If you don't remember all those, then you may have to do those as well through the direct proof, which come from the integral computation. That was for expected value, and this was for variance. I hope everybody recalls all these. Now, because of that, we can say any normal random variable x can be represented in terms of standard normal random variable z through this formula, x minus mu over sigma. You see, capital X is less than small x means capital Z is less than x minus mu over sigma. This is z coming from here. So let's discuss this aspect, x minus mu over sigma. Okay, here we go. Suppose that the mean and the standard deviation of a normal random variable x are as follows. Mu is 16.75 and sigma is 451, excuse me. And all right, calculate this probability, and calculate this. Now, if you draw a normal random variable associated to this, you're going to get something like this. Let's see, we have x-axis like this, and then a normal graph like this. Lousy picture, but please forgive me. And then centered at the mean 16.75. This is what you're going to get. And then less than 16.01 is something like this. 16.01 is here, and then this part. Lousy drawing, please forgive me. Does it make sense? And this can be calculated through standardization. How? Z is x minus mu over sigma, of course. The formula number 1 of this course. Let's see how it goes. Here, centered at 16.75, 1601 is here and shaded to the left. And then if you standardize it, z is x minus mu over sigma. So calculate it. X is 16.01, mu is 16.75, remember? And sigma is 0.451 there, and calculate. What do you get? You get negative 1.64. And if you draw that, negative 1.64 is here, 0 is there. We have corresponding standard normal in the right. You don't really have to draw two of them, by the way. I just draw two identical except for labeling, just because I'm a teacher, so I have to be perfect here. You don't have to draw two. You need only this one. So 60.75 is here in the middle, and that should have been specified actually. Here in the middle, 16.75 should have been specified here. 16.5 is here, 17.0 is here, so yeah, 6.75 is here, you can see that. But it would have been better it was labeled here as well. And then 16.01 is here, we have appropriate shading. And that corresponds to z-score of negative 1.64. Look up the table, we already did. And that's a probability that comes from the z-table. This problem, by the way, corresponds to this problem here. Remember this one? How about the next problem? Greater than 17.03. Okay, 16.75, 17.03. If you draw the picture, you're going to get this. 16.75 is here, 17.03 is here, shaded to the right. If you standardize it through x minus mu over sigma, x minus mu over sigma, you calculate it, you get this. So what do you get? You get the probability that z is greater than 0.62, which we did already. Remember this problem? This one. And this corresponds to this picture here. And this one is the original. You don't need two pictures. This one, the left-hand side, this one is sufficient. And then here we have two x values, x1, x2, and we want the middle part. So we need two z-scores, z1 and z2. Both are coming from, of course, z computation, x minus mu over sigma. X minus mu over sigma. So what do you get? We need z-score between negative 1.64 to 0.62, which we did already. So appropriate subtraction give me this area here that we are looking for. Inverse computation, is this necessary? Well, okay, let's do that. For example, how about this one? We already discussed the inverse for z. So here we go. You see, from the original here, let's see, centered around 0, and then this is standard normal, p is 0.25, so z-score, you can find it, and you did it already, negative 0.675, and that's your z-score. So z-value, x minus mu over sigma, is negative 0.675. It's basically this problem where mu is 16.75 and sigma is 0.451. So what is this? Nothing more than a simple linear equation, numerical linear equation. You can use calculator, or as I did before here, I can solve it symbolically and then plug in numbers. I could do that too. Either way it works. So when do we have 25th percentile? 16.4458, well, approximately speaking, that is. I didn't specify the number of decimal digits, so let's leave it at that. Okay, all right. We went through a lot of. No, we have enough time, so let's do just one more. Let's do this one, the last one here. So, axis between negative x and positive x is 0.95. This is not right. Never mind, this is a wrong problem, so I don't worry about it. Sorry, the one I wrote originally is wrong, so I better not worry about it. Let's just go to this problem, problem C. So the probability that we get bigger than the mean, 16.75, and less than x is 27.5%. So what is my x value? That's what we're looking for, right? So greater than the mean, but less than some x value is 27.5% here, the red region. But in order to look up the table, I have to shade entire left-hand side, so I have to add this one as well. So what I have to look up is not 0.275, but 0.775. So what is my z-score for 0.775? Let's see. Look up the table. So 0.7734, 0.7764, somewhere in the middle. So 0.755, isn't it? Too many 77, so it's confusing, I know, but here 0.773, 0.776, 0.775 is somewhere in the middle. That's a probability. And as for the z-score, 0.755, somewhere in the middle. So the z-score this one, oh come on, this one is 0.755. And then x minus mu is 0.755 times sigma. And then flip this mu to the other side as well. So we get this. And that's going to be equal to, let's see, 16.75 plus 0.755 times 0.451, and run your calculator, you're going to get something. By the way, all these should be approximate equality because nothing is accurate in statistics. So for the formula, this is correct, but otherwise, they're going to be all approximate equality signs. And if you do your computation, and you're supposed to get 17.09. Okay, so much for section 2 of this notebook. We are going to talk about section 3 in a separate